All right, physics reaction video number 52. How exciting. You could watch one every week of the year. Let's see, I did a search for, actually, I think honors physics filter by this month. Anyways, here we go.
Electromagnetic waves.
Oops, let me start it again.
All right, today we are doing a honors unit as part of unit 3 that is only for honors. We're going to be talking about the electromagnetic spectrum and electromagnetic waves.
Cool.
So some vocab to start.
So the introduction about special units for certain students or certain sections, it's really interesting to try to think about how you make choices about that. Sometimes it's, well, I'm not going to test you on it, but, which this might be. It might be, I'm going to test some of you on this, but not others. And that's fine. I mean, none of that bothers me. I think that the struggle is, man, I wish everybody had seen that so that, next week when we hit whatever, it'll make a lot of sense. So I actually think the biggest struggle for me when I do this kind of extra stuff is not this, frankly, not even really like how do I go about it. It's really making sure that I hold fast to that decision, a week from now, 2 weeks from now, 3 weeks from now, when I remember, oh, shoot, that's right, that person didn't see that. So it's been rare for me, but I've been contemplating what it would be like to teach multiple sections of the same thing. So I know a bunch of physics teachers are like, what? You never do that? Yeah, you guys have way harder jobs than I do, no question. But when it happens to me, it tends to happen in lab. And so I will get back into the lecture. I'll say, hey, remember in lab when we saw this? And, I'll get some vigorous nods from the students. And, and finally, some student will be, we have no idea what you're talking about. I'm like, oh, that's right. I only did it in the one lab, right? So I want to learn, especially from high school teachers who do this all the time to try to figure out what's the best way to go about doing this kind of thing. All right, let's keep going.
Start. The electromagnetic spectrum is a continuum of all the electromagnetic waves that are arranged according to frequency and wave.
Just want to stop right there. As students start to get exposed to modern physics ideas like quantum physics, for example, they're encouraged to sort of call into question everything. And this word here, this word continuum, is the word that is constantly under attack from when we talk about the quantum nature of things, right? So energy levels, there's only certain energy levels allowed. Light is you can't have just any old intensity of light. Well, I guess you could have any old intensity, but you either pick up an entire photon or you don't, right? So it's one photon at a time, not a fraction of a photon. And so I wouldn't blame students for thinking that maybe everything is actually quantized. Maybe everything is sort of like digitized, right? Just like the screen you're looking at here has pixels. It's rare that we can actually get close enough to see them. So this is a really interesting question, right? Why could you blame a student who says, oh, I bet you that's not really true? I bet you that actually there's finite spacings between the possible wavelengths, right? We hear about the Planck Scale, right? The smallest space scale that makes sense in some theoretical formulations. I gotta be honest, I don't know a whole lot about that. So please educate me if you understand about the Planck Scale. And so is it legitimate to say that if you know for sure the wavelength of one wave, that the next possible wavelength, because it's a measure of length, has to be at least one Planck scale longer or something, right? I mean, it's so fascinating to think about the questions that we start to engender in our students' mind when we start talking about the weirdness of, it's over a century old now, right? 20th century physics. So anyways, that caught my ear. Let's back up a little bit.
Electromagnetic waves that are arranged according to frequency and wavelength. Now, what are electromagnetic waves? Also called EM radiation or EMR. This is a form of energy that is either emitted or absorbed by charged particles, and it exhibits wave-like behavior as it travels through space.
I love this. I really love what's going on, but I sat here thinking about this by charged particles business, right? So it's not really a problem. The entire universe is made up of tons and tons of charged particles. So this can actually do the trick, but the emission comes from charged particles. I guess so, right? I'm thinking about like black body radiation. We just say that things that are hot emit radiation. But what's going on microscopically? Can every single photon be traced back to an energy transformation of a charged particle. Yeah, I think so. Same with absorbing. So isn't that interesting, right? That my light bulb is hot, and I'm getting some light from that. You're telling me that's from charged particles? Well, yeah, right. So I love this setup, right? It's really making it seem mysterious, and yet surely she's going to get to everyday examples that we use all the time.
So as part of the electromagnetic spectrum, we're talking about light. When electrons, all of the electrons for an element, are in the lowest possible energy state, we call that the ground state. And that's what we've been working with so far.
Cool.
So as an example, we have helium. The electron configuration is 1s2. And this is our Bohr diagram with the nucleus in the middle and our 2 electrons in the first energy level. Now, if we add energy in the form of light, heat, electricity, any form of energy, if the right amount of energy then is absorbed by an electron, then it can jump into a higher energy level. This is unstable and only momentary, and it is called the excited state.
Just want to pause right there because I was teaching, must have been modern physics or something, and I said this exact sentence, right? It's unstable momentary condition called the excited state. And I don't know if a student brought it up or if I started thinking about it, but right, we had just done a unit on I don't remember exactly what order we had done things, but we had talked about the quantum energy levels that are allowed in a state, whether you're talking about the hydrogen atom or I guess the helium atom, although that's a lot harder, or you're talking about, these artificial homework problems like a quantum well, the square wells, that kind of stuff. And we had said these are the allowed energy states. The particle can only be in this, and this. And so we drive that home like crazy. And then we try to drive this sentence home, right? And I remember I was in class and I paused and I was like, well, that doesn't make sense. We have just been cramming into our students this idea that every energy state, it's the allowed energy states. In fact, did she say that? Well, she has this word here, this right energy, right? It's one of the allowed energy states, and yet it's unstable. And it finally hit me. I think I was talking to a chemist friend of mine. It's actually when they're in an ensemble. It's actually when you have a bunch of them that you get this notion that they're much more likely to fall back down again. So an isolated atom, one single atom, would be perfectly happy in this energy state. It would be stable for years, right? It's only if it can interact with a collection of brethren and they have to sort of obey the laws of thermodynamics, which they're not obeying laws, they're just doing their thing. But them doing their thing microscopically adds up statistically to our laws of thermodynamics. So I'm fascinated by the fact that this idea, which we use all the time, the lowest energy state is the most common state, the Boltzmann distribution. I even have a blog post about the connection between that and the electrical college. Anyways, we use it all the time, but it's not actually, strictly speaking, the case for an individual lonely atom. So I ask you guys, do you want to open that very complicated, nuanced door when you teach this stuff, or do you draw pictures like this too and make statements like this too? So I'd love to hear about sort of that partition of ideas that we use when we teach.
So what we had happen was our electron that was right here jumped to this energy level. So the new electron configuration then in the excited state is helium.
So those of you who really understand quantum mechanics well, I'm asking you a question. This jump, we certainly talk about it going into a different shape state, a probability cloud. But I think, correct me if I'm wrong, that the absorption of a photon is an instantaneous event. The reason I think that is because of all of the work that I've done in something called high harmonic generation, where we needed all the photons to hit the atom at literally the exact same time, because if we didn't do that, we were in trouble. This jump here, this physical jump, is supposed to represent the fact that it's now in a different orbit. But because when we think of probability clouds, all the probability clouds overlap at least a little bit, right? The instantaneous absorption of the photon, I believe, instantaneously changes what orbit that it's in, orbital cloud or probability cloud. But I actually don't think. Well, I guess God, when you're talking about probability, you can't talk about position overly well. So yeah, this is a very, very common thing. I think it's going to help the students understand, like, okay, well, they go, oh wow, oh my gosh, they absorbed that photon, and look, now it's up over here. And you might think about, for example, planetary dynamics. Could that happen with a planet, that it suddenly boom comes up over here? Well, in planetary dynamics, you fire off a rocket booster and you immediately go from, let's say, a circular orbit to an elliptical orbit. So instantaneously, you're in a new orbit. But I think your location is usually considered to be at the same place. Go watch The Expanse. So again, my question for you, I mean, I love what she's doing. She's driving home the fact that there's some really, really interesting dynamics going on in the atom. And she's using these cartoons. I mean, good Lord, probability distributions are hard to draw. It's super hard to convince students are things. So I don't see a big problem with this. But the way that these orbits are drawn, especially because they're both S's, right? To draw S orbits as circles is what everybody does. And so, how much damage is this doing? I guess is I'm asking a question. I don't think she's doing any damage, but my brain is just like firing off with all these ideas. So I'd love to hear you guys how you, again, this partitioning of ideas, right? You build up these small models, and then later you say, well, actually, that model that we did, let's revamp that. And I would love to have these students in class a year later, 2 years later, to say, hey, remember when we talked about it this way? Yeah. Well, let's think about what that really means now that we understand even more the dynamics of photons and electrons. So, right, to have them recall their own mental models and realize, oh yeah, boy, there's some problems there. I think that's a fantastic learning experience. Some people claim it's the only time you ever learn anything is when your models are challenged and you're willing to see them with open eyes. Very cool.
Electron configuration then in the excited state is helium, 1s1, 2s1. Okay? Now this is unstable, right? Because we know that we have to fill this full ring before we move on to the next. So it's only momentary that this happens. When the electron falls back to a lower energy level, a more stable orbital, okay, then it releases that extra energy as light. And this is the emitted light when that electron went back down. So here we have our emitted light. That explains the colors that we see in the emission spectrum.
Cool.
In another example, we have lithium. Lithium has 3 electrons. We have 2 in level 1, and it has 1 valence electron in level 2. This is called the ground state. Now, in the excited state, what?
So why do we think there's a buzz in the audio when she's writing on the screen? Isn't that weird? What sort of electromagnetic issues are being caused there? I see where she's going here. This is a super, super cool thing. But let's just talk about a lot of the really interesting things here. First of all, the spacing of the lines changes. Has she really driven that home? I don't know, right? But, would a student say, whoa, what the heck? Why did you draw these? Why were you so lazy with your drawings, right? So there's something really, really teasing about that. Number 2, very simplistic. She's not even doing S's and P's and D's and F's anymore. She's just doing 1, 2, 3, 4. And the physicists in the world are saying, yes, I hate all those S, P, D's, and F's. Let's just do numbers. But here's a really interesting question. I think what she's going to start doing is drawing this third electron as being maybe here, and then maybe talking about it falling back down or something, right? I think that she's got a little setup here that she can talk about lots of different transitions that could generate light. But it's fascinating, right? When I first saw it, I thought, okay, this is lithium. And I thought, oh, helium, helium, helium. Why? Because I only saw 2 electrons. But it's actually, I think, now that I've thought a little bit more about it, I think that she's really saying, leaving some space. She's about to draw that third electron. So how do we deal with sort of showing students our setup without explanation? So I was just a part of a conversation about Zoom meetings versus group meetings, and people say, well, Zoom's nice because you can get yourself fully set up while everyone's in the waiting room, and then you can let them all in. And in Google Meets, you sort of have to let them in when they come. And if you're doing any sort of setup, they can see it. And of course, in physical classrooms, we have the same problem. Do you ever shut the door to try to get everything set up before you let all the students in? Versus just having to be in there. I do a physics show, nail beds and tug of wars and stuff like that. And every once in a while, I have to do my entire setup while the audience is sitting there because they're in some sort of, school presentation thing. And I have to be kind of behind the principal setting all my stuff up. And it kind of stinks because I'd love to hide the nail bed, for example. I'd love to hide the liquid nitrogen. I'd love to hide the things that they just can't wait to see. But, as I so often say, I'm so interested in flexible teachers. So how much is this a problem? Obviously, she's going to get there. It's not, in the long run, I can't imagine this is a big deal. But could you imagine a student who's just like helium, 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 and just has a focus that these are helium, and suddenly you draw a third electron, and how can helium have a third electron, right? So do we worry about that? Do we prep them? Do we think about them? What do we do?
What happens is if we have enough energy added to that electron, so we're adding an electron, then that electron will jump
Cool.
to a higher energy level.
Cool. That was awesome.
Remember that this is only momentary, so when the energy then goes back and releases that energy, the electron falls down back to the ground state, and we have a release of energy.
Cool.
Or what is light.
Cool.
Yep. Now this is actually the same way that an ion is formed. If energy is added, and it's enough energy to actually remove that electron, then the electron is stripped and we have lithium with a +1 charge because it's lost this electron.
Super cool. I love that last piece. Notice, by the way, that last piece is dependent upon these spacings getting smaller and smaller and smaller, right? Because if these just kept on going, this is a really weird statement, right? Like, well, imagine if these were evenly spaced and the students were led to believe that there's no end. There's no vertical height end in sight. So then she would say, oh, well, there's enough energy to get it to go up maybe to some energy state beyond. But they might ask, well, why did it ever stop? Right? There's no magic about n equals 7, though the seventh harmonic in music sounds like crap, so don't use it. For you trombone players that don't play that A flat in first position. Here's what I wanted to talk about, though. Again, subtleties, right? Again, something they might see a few years in advance. So imagine the electron, let's say I'll just pick on this one here. Imagine it got enough energy to go right here, right in the middle between 3 and 4, right? Well, it's not allowed to be there. So some people say, oh, it won't absorb that. Never mind, it won't absorb that. I struggle with that because I actually think it does absorb that. It absorbs that. It immediately, instantaneous, 0 time, re-emits it. And that's how scattering works, right? Same color light goes in and out. If it goes halfway up, it immediately gives it back again. That's how high harmonic generation works. I can give this, imagine that from here to here was 11 photons worth of energy. Well, that's how high harmonic generation goes. We go ding, 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 and we can get it to go all the way up there, right? But if we go 13, ding, 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 we can get it to here where it's not allowed to be. So it gives it all back to us. That's how high harmonic generation works. So I'm really intrigued by the subtleties here. And again, this is too much for her students. And again, the notion of it needing to be a thermodynamic ensemble is dependent upon a lot of this. So, but I really, really loved what she was doing here, this ion formation. I love how it's technically tied to the spacing of the energy levels. It's super, super subtle. And, I think she's ready if a student were to ask a question. Ooh.
To understand this a little better,
Actually, I just want to go back. There, I'm actually going to stop here because if she's going to shift gears, and we're about 20 minutes in, so I really loved what she did. Number one, she did her own handwriting, and then flipped to this. That was super cool. I think that really driving home what's going on of raising the energy levels and lowering the energy levels is fascinating. I threw several curveballs that come about from much more advanced physics that likely she's not going to cover in her class, but I'd love to hear from you, like that partition of ideas. It's super interesting. So really cool stuff. All right, everybody, have a great day. And remember, physics teachers are awesome.